Okay, geometry, we're going to take what we've learned so far in this group of lessons and apply it to similarity transformations and start talking about similarity of shapes. So first of all, observe figures 1 and 2 and the images of intermediate figures between them. Figures 1 and 2 are called similar. What observations can we make about figures 1 and 2? Like, what do you guys think? What can we talk about? I mean, I can say they look alike, right? They have the same shape. Not really the same size. And if we think about an actual definition, we can say a similarity transformation or just plain old similarity is what we're going to be calling it, is a composition of a finite number of dilations or basic rigid motions. The scale factor of a similarity transformation is the product of the scale factors of the dilations in the composition. We're just going to make it one scale factor from beginning to end. And if there are no dilations in the composition, the scale factor is going to be 1. Okay? To continue that, two figures in a plane are called similar if there exists a similarity transformation taking one figure onto the other. Okay, I would, if you want to copy in your classwork, write down what we just did in the above slide for a definition. And characteristics. We can say that similar figures should look the same. But one could be a different size. It could be flipped. It could be rotated. It could be translated relative to the other one. Okay, an example would be, oh, I don't know. It's hard to do with this awesome pen. Okay, but if those are exactly the same, just smaller. Or I could have turned it upside down, etc. Non-examples start out with the same smiley face and make it a non-circle smiley face. Okay? Alright, consider what you know about congruence when thinking about similarity. One use of rigid motions is to establish whether two figures are identical in the plane. That's when we did rigid motions. We would have a series of rigid motions and we would have one figure map onto another figure, and then we would conclude that they're congruent. We can use similarity transformations in the same way. If we look at figure A and figure A prime, we can see that there's dilation. I mean, I could find a center of dilation for those two figures, and we know that any straight lines are going to be parallel in my dilation. So from our work on dilations, we can see that there is in fact a dilation that would map figure A to A prime. Note that a similarity transformation does not have a minimum number of dilations or rigid motions. Okay, that's important. We can do as many things as we want to. The figure A prime, sorry, that should be A prime, was rotated 90 degrees and is now labeled a double prime. Is this a dilation? No, it's not a dilation. We can say that it's not a dilation because, okay, these straight lines aren't parallel. That's our first clue. Remember, we can tell if things are dilations if our lines are parallel. So how would we map A to A prime? All right, let's look at it. we would need a series of steps. Okay. Dilation and rotation. Or we could do, rotation and the dilation. And that could get us A to A prime, or A to A double prime. That would work. And we'll see that in the next few slides. We're actually going to do a similarity transformation to get A to A double prime. A few important things that I want to point out. If two figures look identical, they must be congruent. Not always. We know that they are congruent only if a series of rigid motions maps one figure to the other. It's not enough to say that two figures look like they have the same shape. Okay, we can never use that as a proof in geometry. We have to show that similarity transformation maps one figure to the other to be sure that the figures really do have the same shape. Figures that are similar must be scale drawings. Okay, similar can go to scale. And we have a new symbol. If you remember when we talked about rotations, we would have a little r, dilations, but we have a similarity transformation. We're going to use T just like the translations, but we'll have different little notations sort of subscripted, and we'll see that in a second. So similarity transformations are denoted with a T in the function type notation. The transformations that compose a similarity transformation can be in any order, but we are going to usually begin with a similarity transformation with a dilation, and then follow with everything else. So we're always going to have a dilation first, and then everything else in parentheses on the inside. Alright, so we're finally looking at A to A double prime. So if T is a similarity transformation, then T is the composition of basic rigid motions and dilations. The scale factor R of T is the product of the scale factors. And then with respect to the example that I sort of cut and pasted above, we see the similarity transformation of A is what we did first. We go on the inside. We dilated about center O, a certain scale factor of A. So we went from A to A prime, a dilation, about center O, and then we rotated it. We rotated it center C a certain degree. This just donates a certain degree. Okay? Please note, if there's no dilation in the same similarity transformation, then it's congruence, and your scale factor is 1. Alright, so here's another example. We have figure Z prime similar to figure Z. Describe a transformation that maps figure Z onto Z prime. Okay, on the next page I'll show you the picture, but first I have a dilation, and it looks like I got smaller, so my scale factor is going to be less than 1. And then next it looks like I have a reflection. So that would give me, my dilation is going to give Z to Z1. My reflection's going to give me Z2, Z1 to Z2. And if we look at that, first I got smaller. Okay, we could see that it would get smaller. Then it looks like I flipped it right over a line. And then a translation. Gives me Z2 to Z prime. And we could call that Z3, which we'll see in the next slide. And then for a rotation until Z3 actually coincides with Z prime. So what I'm going to do down here, oh, I can't erase it. Give a Z3 there. Let's look at it. So let's look at it. First it looks like I got smaller, okay, to Z1, and then I reflected it over line L and got to Z2. Then we did a translation to get to Z3, and then a rotation to get back to Z prime. And actually those are all the steps written out for you again. Okay, let's practice function notation. So exercise 1 through 3 give us the opportunity to practice describing transformations that map an original figure onto its corresponding transformed figure. So figure 1 is similar to figure 2. Which transformations compose the similarity transformation that maps 1 onto 2? So first let's dilate. And let's see, did we get smaller or bigger? Looks like we got bigger, so our scale factor is going to be bigger than 1. And then it looks like we just need to reflect. So figure 1 to figure 2. So first I dilated, it got bigger, then I reflected over a line, and I made it to figure 2. Figure S is similar to S prime. Which transformations compose the similarity transformation that maps S onto S prime? Let's see, I'm going S to S prime. Excuse me. Looks like I got bigger, so the first thing I'm going to do is dilate with a scale factor bigger than 1, and then just a nice rotation. Can't spell. And I would say around a center C. A degree that we don't know because we're not measuring it. So we call that a degree of theta. So S coincides with S prime. Okay, for sake of time, I'm going to move on. I think we've got it. Example 2. Just 2 things I want to point out. We need to measure some things when looking at example 2. So to show that no sequence of basic rigid motions and dilations take a small figure to a large figure, we need to take measurements. And if you look at this one, all I did was I would measure, let me get my highlighter out. I measured here and compared it to there and said, okay, that would be about a scale factor of 2. But then I measured just AB and compared it to just CD, and we would have a scale factor of about 4. In that case, we have no similarity. Here, if we measured segment AB and compared it with segment WX, it's getting smaller, so we have a scale factor of approximately 2/3. But then if we check the other segment, CD compared with WZ, our scale factor is about 1/2. So again, with this example, we goodness, we have no similarity. And we're not solving this, we're not deciding on this just by looks. I mean, this one does look a little bit skinnier. We're actually deciding it by measurements. Okay, the scale factor needs to be the same. All right, what purpose do transformations serve? Compare and contrast the application of rigid motions to the application of similarity transformations. I'm going to sketch a few answers and I'll be right back. Okay, all transformations compare figures in a plane. We know that rigid motions are distance preserving and dilations are not distance preserving. Okay, compositions of rigid motions. We use them to determine whether two figures are congruent. That would be composition of rigid motions. And then compositions of rigid motions and dilations to determine if figures are similar or not. And that's it for today. We'll see you tomorrow for the problem set.